No. Hello, welcome back to DAGM GCPR. This is the second part of the special invited talk session of GCPR. And it's my pleasure to announce our next invited speaker, Bernt Schiele. Bernt is a Max Planck director at the Max Planck Institute for Informatics in Saarbrücken and a professor at Saarland University. He received his PhD from the Institut Polytechnique de Grenoble in France, where he worked on object recognition using multidimensional receptive field histograms. After he finished his PhD, he was a postdoc and visiting assistant professor at MIT, and then joined ETH as an assistant professor. Between his time at ETH and starting his position at the Max Planck Institute in 2010, he was a full professor in the computer science department of TU Darmstadt. Bernt is very well known for his work on pedestrian and object detection and tracking. And if you're working or have anything to do with semantic segmentation, you'll most likely have used his Cityscapes dataset. And today, Bernt is going to talk about challenges and opportunities for robustness and security in computer vision and machine learning. Bernt?
Yeah, okay, thank you very much, Thorsten, for the introduction. It's a great pleasure being here. Thanks very much for the invitation. I really think this kind of setting, having a half day of some sort of invited talks, is very nice to have as an addition to GCPR. Right, so as Thorsten said, I want to talk about challenges and opportunities about robustness and security. And in a way, sort of, I want to briefly, briefly say what I mean by that. So obviously, we all use machine learning models these days. Right? There's some data that we start using to train some machine learning model that does, for example, semantic augmentation in the ideal case. But now, what's the problem about security, right? So one of the things is the most well-known case, I suppose, is if you have an input variation like adversarial perturbations, but even if you have just some noise or some other small change in the input, right, your model might not do what you really want it to do. So, and that's sort of a problem if it's attacked by sort of an adversary, right? You're talking about security. If it's basically just sort of a variation that actually is caused by some noise or some other input changes, right? You're talking about robustness. So these two things are really very much related for me. So it's really robustness security is sort of a very interlinked topic to me in computer vision and machine learning. So that's one of the things. And I'm going to talk about adversarial perturbations today, actually. Another topic, however, that is related and that I'll talk about here in terms of security is actually about the ability to steal actually machine learning model directly just by observing some of the outputs. And the question is, how many outputs do you need to observe, right, to really steal the complete functionality and basically making sort of, the one that actually learned with a lot of efforts, the machine learning model, basically sort of obsolete, or at least sort of putting in the worst position. Other problems that I'm not going to talk about today is, for example, membership inference. The problem is, how much can you infer about the data that was used to train the model, right? Can you reconstruct, for example, in a pedestrian detection setting, can you reconstruct the individual faces that were used actually for training that model, right? Again, invading in that case privacy of the respective people, which might not have known that they have been recorded in the first place. So these kind of things, right? We really, I think we really should think more about these issues that are there, right? And ideally, our models are secure and robust to all these problems. And at the end, right, sort of all these attack surfaces, as the security people tend to call these things, we really should start considering more in our own daily work. What I want to do today is to talk about two specific issues related to this broader topic of robustness security. And the one is about the bright and dark side of scene context. And I'll get to that next. And the other one is actually literally about this, what I already mentioned, this reverse engineering and stealing of deep models. And in each of these cases, there's a series of papers that actually are underlying the parts of the talk that I'm talking about. Let me start about the scene context problem, and let me start with this NeurIPS and the GCPR paper that we had, in particular with Rakshit and Mario. So what's the problem about context? So yeah, here's really sort of an exemplary case that tries to illustrate the problem that context might cause. So here is sort of an image, right? That is some original image, and sort of some state-of-the-art methods like UberNet gets actually a pretty good result here, finding the cars here, the building, road, and the sidewalk here. But then if you do actually a context change, in that particular case, we remove all the cars here on the left side of the road, all of a sudden, UberNet actually doesn't do well anymore, right? Actually, in particular on this right side of the this image right here, it doesn't see the sidewalk anymore on the right side of the road. And it's kind of, if you think about it, actually, it's quite logic, right? So if there is no cars on the left side of the road, it's actually less likely that there's a sidewalk on the right. And that's sort of a co-occurrence of classes that happen in the data set, right, that we tend to use. So in that sense, it's not unreasonable to make that inference, but actually it's overdoing it, right? So it's overdoing in the sense that it actually doesn't really see the sidewalk anymore properly or very, robustly anyways on the right side of the image. So here's really an overuse of context. We have learned context is extremely helpful, right, for doing certain vision tasks like semantic segmentation or object recognition or detection, but really our current models are overusing it. That's sort of one of the starting points that we had in this work by trying to understand how much actually these models really rely or too much rely on scene context. In particular, we started looking at a particular aspect of context, which is co-occurrence of objects. So we basically, as for example, taking away sort of the cars on the left, see actually what happens to the sidewalk on the right. And we wanted to quantify this context sensitivity. And then also, once you identified problem cases, you can use those problem cases that you identified during training as data augmentation for your, again, during training, and hope that actually in that way you basically improve the overall performance and become less context dependent or less sort of prone to those context issues. So I'm not going to talk about the technical context, but an entire NERSC paper about how exactly to remove objects. The way we do it is actually that we have sort of, we are giving just a keyword, right, to an image like this one here, and then the system is supposed to learn basically where the object is, in that particular case, the dog, and it removes it, right? So it's really sort of an in-painting task without knowing where the respective object class is. And again, I'm not going to talk about the technical details, but you can do this quite well. And here are examples here down here, as you can see, that all of them are perfect. Here you see there is some smearing going on. But since we're using this essentially for data augmentation during training in particular later, it's not too bad if there's, as long as it actually generalizes to real world images that actually really are similar, having similar kinds of context changes. So in a nutshell, right, sort of in order to test things, we're basically taking an image like this one here. We know what kind of objects are in here. For example, there's a monitor in here. We're removing the monitor. So here's the monitor removed. And then we look how well the target model does on this one, right? So here, once the monitor is removed, it should still find, for example, the laptop and the keyboard with the same probability aim, right, than before. And if we remove it, right, it should be basically not just reduced dramatically, right? So that's sort of the kind of consistency check we do. And if that's not the case, we're saying, oh, here's a model that actually heavily relies on the context. So let's add this kind of context removed image, right, during training in order to improve the context dependency, or make it less dependent on the context. And we do this with other objects here. There's the keyboard removed, same story. Right, if the object scores of the other objects basically decreases dramatically, this is actually a bad sign. It really should basically stay similar. So what we do is we remove one object and keep the other, and do the vice versa. So and then actually the scores have to be for the one that is there higher than only when the context is here. That's sort of the consistency we do. Okay, so that's the way we're doing this testing, checking consistency, and then the data augmentation. And here are cases now that show basically what this can do. So here again, this original image that I had before, right? UberNet does well in this original image. If we here remove now those cars in the lower right corner here of that image, now actually all of a sudden UberNet does actually hypothesize there's a sidewalk, even there isn't. And then if you have data augmented versions of the data, right, you're doing better here. Here's another case, the case that I showed initially, right? Here, the cars are removed, right, in the second row of those images. UberNet basically has these issues here of the sidewalk. And again, if you do this data augmentation, it does actually better in terms of this classification or segmentation. So here's another quite striking case, I would say. So here we have the original image, right? And here we're removing the trees in the upper part of the image, right? And then UberNet actually does really not particularly well. It really hypothesized there's the Earth. So knowing that there are trees here, right, actually helps it to identify grass, even though clearly the grass is very visible and very locally, clear, right? If you show this to any human, right? So it's really surprising how much that context here basically destroys information. And again, if you do this data augmentation, it does a lot better. And maybe the last example, which in a sense shows really clearly, in my view, what's going wrong here, is that here's the car, right? Sort of on a snowy road. That's sort of a pretty unusual scene. It's somewhere in the tail of the distribution. You don't have too many roads where there's snow on the side, right? It's rainy kind of thing. It's wet the floor and whatnot, right? If we remove the car here, right, all of a sudden the UberNet actually still sees part of the road, but it doesn't do that well in part of the image on the left side of the image. And that really is, as I already tried to say, is in my view, the problem is that it's really sort of in the tail of the distribution. So it hasn't seen enough scenes like those, and the car is an extremely good indicator that there must be a road somewhere, rather than identifying the road on itself and then also saying, oh yeah, there's a car, right, and then actually helping each other, but still overusing the information that there's a car somewhere in the image. And again, here, if you do the data augmentation, you can improve on this. And my point of this particular part of the work is, in my view, that it's really essential that we're getting more to the tails of the distribution. It's not enough to just train on IID data and also test on IID data, because we will be doing okay on the IID data. But then in the tails, we're going to have issues, right? In tails, and this is sort of a tail image, right? This image, in particular, if we remove the car, it's really very much in the tail. And then I have an issue that the system is not generalizing to those cases, even though they're absolutely, classic to encounter than in real world scenarios. Okay, so oops, I'm moving back here forward. Okay, so that motivated us to actually think about this problem even further, trying to generate more images that are really in the tails and potentially even going beyond the tails that we even have in the test data. That's really what this paper in GCPR was about, trying to semantically generate images in an adversarial way that move us really sort of beyond the decision boundary of our current classifier, but then basically still having images that are really sort of semantically plausible for the classes they should correspond to. And this is really the idea, as I already tried to allude to, that's if I only use IID data, sort of independently identically distributed data, during training and test, I might be good, but it actually might totally overestimate the performance. And we're obviously not the first one seeing this. Sort of, there's been people adding noise or obviously changing context, and then the IID validation or test set performance is overestimating the performance. So it's really, the problem is if you only use IID data, it seems not being sufficient to basically train our models for realistic settings. So the way we think about it is we're trying to illustrate it in this picture. So think about, you have a training data distribution, right? And assume your test data is maybe not perfectly IID, but at least it's sort of covering some more difficult test cases that if your decision boundary of your current model is around here, you might have some error cases discovered by your new test data. If it were a perfectly IID test data, you would not even see those. Right? But assume that test data is slightly more broad and getting more test cases. But still, if that is the classifier performance or the decision service, right, and the true class boundary is somewhere over here, there's a whole range of problem cases in the middle, right, which you cannot discover by just having more test data. Yes, you will eventually in the limit find those cases, but it's not very realistic. So why don't we start from a particular training data, trying to generate more and more cases that are more and more difficult for a classifier, really trying to move it beyond the classification boundary of our current classifier setting, and then have those images tested and see if they're actually sensible still in terms of their semantics on the class annotations that we were asking for, but not really performed well. So it's a testing framework, and then also a framework to really generate more samples that can be again in the tails, right? So really the way to think about this, these are really again tail examples, generating more of the tail examples that actually make it sort of easier to train for those tail cases and hopefully generalize better. So the way we do this, and again, I'm pretty high level here to do this, we have sort of a synthesize, and the synthesizer decouples sort of the shape and the appearance. So from a particular training image, we take the shape in that image, right, from a particular class, here the bird, right? But then we are actually using an appearance from that class bird, which we learned it's a latent space, and we have a convex cell of latent vectors in that of that appearance space. That basically is the input here to the synthesizer, which generates a new version of that image with a different appearance of that class. And again, in that particular case, the bird. So there's the synthesizer that is trained on the one hand, and then we have here basically a gun setting. This is then used for the detector. We're getting a loss if it actually does sort of, if we try to really sort of backpropagate the loss in a gun setting so that the generator generates more difficult, more adversarial examples for my detector, right? So this is sort of an adversarial setting, and it's semantic only because we have this constraint of the appearance, the convex hull of the appearances of my particular class. The adversarial representation I talked about, and I said the appearance constraints, these are not hard constraints. You can argue this is not really sort of, you can't prove anything about it, and that's correct. But still, right, we did some user studies. I'm going to briefly talk about those. These appearance changes we're doing are still basically, you know, very reasonably close to the object class, and in that sense, it still does sort of something sensible in terms of semantic preserving semantics. So here's an example just to give you a bit of an idea about this iteration. So we're starting from the original image. So iteration 0, right? Sort of the Bernt classifier is reasonable. At iteration 2, the Bernt classifier is, you know, slightly gets decreased because you'll obviously be moving in sort of the direction to the decision service. So it gets, you know, step-by-step decrease. And here actually appearance has changed quite a bit, right? In this, because we're doing this in the convex hull of the appearance space. And at some point, you're getting some appearance that actually happens to be not anymore consistent with our classifier you know, detection. So here it says dog, even though obviously if we as humans have looked at this, is clearly still a bird, right? And you can move this further, right? So here now it says very high confidence is a dog with a frisbee somewhere in the middle. So that's sort of the kind of manipulation we're getting. And if a human looks at this image, clearly there's no frisbee, there's no dog, there's just a bird, right? So that's the kind of idea. You want to generate images that are more they're constrained semantically, but adversarially for your current detector that you have trained. And here, just to give you a glimpse of kind of the performance we can, you know, do in terms of, you know, reducing detector performance, finding examples that are hard. So on the original data, we have some 81%. I think that's the COCO data. Mean average precision of the detector, if we basically have one semantic adversary, right, on basically changing the appearance of one of those objects, we're getting down to some 60%. And if we do 2, we are getting down to 46 or so percent. And again, we do a user studies for those examples that we're using here. 93% of the cases, humans declare this to be still the same class, right, as it was original, like the bird example I had on the previous slide. So what are those cases, right? And we have sort of looked actually qualitatively, and the kind of most frequent cases are the following 3, right? So the one case we're finding by this semantic manipulation is basically that like a stop sign here actually gets camouflaged with the background. So it's actually the colors are changed and actually merge with the background, and then the detection actually is not anymore there. Here you can argue, is that something you really need to be detectable? I would argue if that's a really dirty stop sign, you really want to make sure that it's still detected. So that's debatable because you're getting to the borders of the problem, right? So of the detector. But that's exactly what you want to do, right? You want to generate examples that are hard for the detector and then judge if they are basically a problem case. We're finding classic cases where sort of an original motorbike basically is then, you know, changed in another motorbike-looking thingy, right? I would say this is clearly rather a motorbike than a backpack. So the backpack classification really is bad here, right? And we're again finding cases where the context actually plays a bit of a role. So here's a person in the air, right? So the person jumping in the air like a skier. And because in the air, sort of behind before the background of the sky, by changing a bit the appearance, right, actually the detector claims it's an airplane, right? So here the context again is overused because we're getting to this tails of our distribution. And so quantitatively, you can also see here the improvements that we can get. So on the IID data, as I said before, that's not necessarily the data we want to target, because the IID data is basically the training and test is roughly okay. Yes, we do slightly better, but that's not that, you know, interesting. And we would not even expect to be much better here because the data is, you know, by design more or less IID. We have this out of distribution data that's the OOD kind of data. We can actually get quite some improvement on the COCO and Pascal setting. But mind that this is now we're trying to find cases, not particularly those OOD cases that exist in those, but you're trying to cover sort of all kinds of cases that are not in this IID data in the first place. So it's really hard to improve this by much margin, right? I mean, this is actually all pretty good numbers, I would argue. But the point is that you really need, or in my view, really need to move more into this kind of setting where we have more of those kind of out of distribution kind of data for testing, and then, you know, improving on those. Okay, so yes, this is all online on GitHub. You find code, paper, whatnot. So what's the part here? So I would argue that sort of scene context helps a lot to achieve better performance. Current models, however, are too dependent. I would argue this quite strongly, actually, are too dependent on scene context. We proposed the testing framework and data augmentation framework, right, to automatically generate more scene context that overcomes some of the limitations here. And we also proposed this new semantic adversarial generation framework in this GCPR paper, in the second part of the first part here, where we try to generate semantically constrained failure cases beyond the IID cases. Right, and clearly there's much more work required here in this space, so I'm not going to claim this is anywhere close to being solved. Okay, so that brings me to the second part, and I guess how much time I have? To have another 10 minutes? Is that okay?
Yep.
Good, cool. Then yeah, I'll give an overview. I can't go into too much detail. So here's about reverse engineering. What's the problem? The problem is, if you actually let me go directly to the next paper here. The setting is assume you have a model trained, right, and you want to monetize it by actually deploying it as an API. Right, sort of then somebody basically can query obviously this and pay some money for you, like maybe a few cents per query, right, and you get some prediction output. So there's really this going on that you want to monetize this this API that you have trained some models for, right? So the question is, can you actually steal the functionality of that model? And that's exactly what this paper is about. This knockoff math paper. And the setting is that somebody who trains the API has some images, that's some intellectual property, right? It annotates it, again, the intellectual property. He has some favorite model, some deep model, again, some intellectual property here. All of this intellectual property, deploys it as a black box model. And somebody who would like to steal it, right? So if somebody wants to, the lazy guy, right? So he has another set of images, just his own homegrown data set, right? He's very lazy. He doesn't annotate himself. He uses the queries just to annotate here, selects his own sort of favorite deep model, whatnot, right, and trains a model. So the question is, how easy can you basically imitate, with this new model, the functionality of the original model, right? That you can basically also sell your own kind of black box prime model, right? The question is, if you don't know the data, right, which you don't, right? You don't know the architecture of the victim, right? And you want to do this with as few queries as possible because every query costs you some money, right? So at the end. So now this sounds very much like distillation, right? Model distillation. We know this actually can work quite well. But the difference to model distillation is in model distillation, we know actually distribution. We know which images are used by the victim. And then the one that tries to copy this, right? The model distiller actually knows that data distribution. That's not the case for us, right? We're using an API. I have no clue what data set that is used here for training. So we really have a different data set that we use. To make the point here sort of pretty obvious, let me tell you really what we literally do is the following. So we want to train a bird classifier, right? But we give it no bird images whatsoever. We give it sort of all kinds of images here, some trains, some dogs, some bicycles, you name it. You do all kinds of images. Like we do this pretty systematic sort of your very random images or very different images. We're getting some posterior vector here from my bird classifier. And then we use those pairs from those random images with the bird classifiers. And we train what we call the knockoff bird classifier, which is sort of the stealed model. And then we apply to real bird images, and then we actually get pretty good bird classification. So it's really sort of not using any images related to the domain still allow me to basically do something on the domain. It's, I mean, very extreme. That's typically not what I would do. But the point is, I can do this surprisingly well. And that's exactly what the paper is about, how good I can do this with even very unrelated images. So the setting we had, we looked at 4 different data sets of Caltech, CAP, indoor, and diabetics. And the diabetics data set was exactly there. I trained sort of on diabetics images, and all of a sudden I can do bird classification, which sounds very strange and very surprising. And that's actually really true that you can get surprisingly far, that you only use diabetics images, you still can do bird classification once you have this trained with the posteriors. Okay, so how does that work, right? So here, in sort of, don't look at the numbers. The overall, ballpark thingy is that we can basically obtain about 80% of the performance of the original victim spawn, right? Sort of an API with sort of, let's say 9%, right? And then you get 80% of the 90% if you train this, right? Depending on the particular setting, but roughly that's about the number you can get with relatively few queries. Now the question is how few queries? So here's the budget of queries, right? From left to right. And you can see here, I can do with several 10,000 of queries, I'm basically recovering the accuracy, right? And if I do something a bit smarter, a bit more reinforcement, kind of active learning type style, I can reduce this by, again, an order of magnitude, roughly speaking, right? So I can do this all reasonably efficient. So in only a few thousand queries, right? Think about a cent or something you pay for it, right? A few thousand is really just a few $100, right? It's not a lot of money really if you want to, if you do this with a standard API. Does it translate to the real world? Well, an API that is not to be named here, we actually did exactly that experiment. We basically queried a set of images and withdrew sort of the posteriors and used that for training our own model. And yes, we could basically imitate with the same level of quality, roughly speaking, again, 80% or so, the performance of that API that somebody tries to really sell for money. So now, is it possible to defend, right? That's sort of the question that's sort of lingering, right? How well can I defend? So far, I only talked about using the full posterior vector. So what happens if I only use the argmax? So only the argmax output, right? And yes, this is the violet line. So the red line is if I have a posterior vector. The violet line, basically, yes, I reduce the performance, but it's still increasing. So it basically delays the problem. So instead of a few thousand, I maybe need a few 10,000 queries, but it really isn't sort of preventing this whole problem, right? So it's reducing sort of this problem, but not elevating it essentially, right? And we have different things. You can be argmax, you can top K, you do rounding, you add a bit of noise. All these things work a bit, but they don't really prevent this. And that's sort of the last bit I want to briefly talk about is this iClip paper from this year, which we call predicting poisoning, where we now basically add explicit noise into the outputs in order to prevent this kind of training. So the setting, and that's sort of, again, just in a nutshell here, one picture here, you have this, that's the normal model that you would have, right? It gives you some output. Now we basically, in order to defend this, we're adding some delta, you can think of this, some perturbation, some adversarial perturbation, if you like. And this adversarial perturbation should be such that sort of as on the utility side, if you sell your API, basically it has still about the same accuracy, right, as before, right? So that you're basically not losing performance. If you want to still sell the API, to give some, sensible results. Another metric is that sort of the L1 norm, for example, should be not that far away. You want to be, small in these changes you're adding. But then on the other side, the adversary should not be able, or at least sort of should have a hard time to imitate, or when he gets this, so perturbed outputs, it should be very hard for the adversary to train a model. And the classic way this is done, you're having a shadow model. So you're training sort of not just our own model, but also train a shadow model that uses those outputs here. And then you basically, when we see the shadow model, we get a gradient, and using that gradient, we're trying to generate, we manipulate the output such that the gradient becomes a maximal angular deviator from this. That's why we call it maximal angular deviation algorithm, so MAD algorithm, where basically just to add in the delta such that the angle, the derivative basically really goes in the wrong direction. Ideally, 180 degrees in the wrong direction. That's not quite possible all the time, but at least you're trying to really change this output as much as possible to really fool the adversary's gradient. And again, for this, you need a shadow model trained simultaneously. It's pretty expensive, actually. Okay, so what does that give me? So here's the performance, right? So here in this corner, this point here is the performance if you just give the performance of the defender, so that's the API, right? So having a certain performance, the attacker, right? The adversary here gets a certain performance. So ideally, you want to be up here in the upper triangle as much in the left corner, because then the defender gets as much performance and the attacker doesn't get much performance. So if you add random noise, it turns out actually, yes, you can reduce the attacker's performance to a certain degree by just Gaussian noise, but then you actually go below, which is worse than because then the attacker gets much better performance than you're with the API. That's exactly what you not want. And this algorithm I briefly talked about, sort of this maximum angular deviation, now basically delays this kind of problem by a certain degree, right? So you can go up to here, roughly speaking, where you still preserve quite some of the performance, right? And actually you really decrease the performance of the attacker. So here, this orange line is yet one more line where we also do this maximal angular deviation, but we preserve the argmax. So here you basically literally preserve the accuracy, right, on the original data, simply because by design you don't change the argmax, but you're still adding sort of more perturbation on the rest of those posterior other components of the posterior vector. So you can really reduce this, but as I said before, if the attacker knows you're just the argmax is still the same, he can still use just the argmax, and again, he's back in business. So it's not a particularly realistic setting. So let me conclude. So clearly, models contain lots of intellectual property, right? So if somebody wants to attack it, right, it's actually it's really important for those who deploy them that there can't be attacked as easy, right? Even I didn't talk about this, but one other setting is if you're just looking at the outputs, you can actually train a classifier which tells you about if dropout was used during training, if sort of the max or average pooling was used, the activation function, the number of layers, all kinds of things you can estimate. I haven't talked about this here today, but there's another paper about this. And obviously, you can also directly steal the functionality with only a few $100 essentially, right? That's the bottom line of this GCPR paper from last year. And as I already made the point, it's very hard to defend, right? In these what I call the passive defenses, just noising, doing top case, something very simple, easy things are not working particularly well. But then this active defense that I just talked about for the ICLIP paper from this year, it's more powerful, but it's very expensive, and it's not clear how much it really sort of helps in the long run to really defend things. With that, I'll thank you very much for your attention and looking forward to your questions.
Thank you very much, Bernt. We have multiple questions from in the Discord channel. The first one is on the first project where you remove objects and then do in-painting. And one question there is whether the in-painting itself could trigger some of the fault segmentation, whether you looked into this.
Yes. Okay. So there's really two modes, right, where we're using this. The one mode is for identifying failure cases, and here, obviously, if we do in-painting, as it will never be perfect, even though you would argue that they're reasonably good, but they'll never be perfect. You can obviously find failure cases that are only due to the artifacts we're getting. However, as I made the point, right, we're also using those images, right, for training. And then the testing is actually on real data. That's why we looked also at this OOD data, right? This out of distribution data, right? And that obviously these are real images, right? We're generating those out of distribution images, drawing training, right? Using them to augment our training data, and then we test on real images which are not manipulated by us. And so in that sense, obviously, yes, I haven't really talked about this on the very first part of the first part of the second part of the first time. So I had this ECCV paper, right? So I talked explicitly about these numbers, and we have all those such numbers in the Non-Replicability paper, right, that actually are about this.
Thanks. Another question is again on the first part, and Carsten Rother asks whether you visualized an object-based tree, like a causal tree. For example, if you remove cars, this affects grass and road. If you remove grass, this affects something else. And he is interested in understanding whether things classes affect more stuff classes and vice versa.
Yeah, that's a very interesting thought. We have thought about this, but we haven't really done this yet. So we really only looked at co-occurrence of things, and we basically looked at the co-occurrences in the data, and then basically looked at cases that are more or less frequent and explicitly searched for cases that are, likely to cause problems. But we haven't had any causal graph here. That's absolutely an interesting direction. The problem we had, to be honest, is that these data sets, if you start looking at co-occurrence of things or co-occurring of co-occurrence, sort of triples of something, then you're already getting very, very sparse in the distribution. So I think the current data sets, even something like cityscapes or COCO, are still relatively small to these kind of analysis. So I think we would need, an order or two orders connecting to larger data sets to really do this properly intuitively. But absolutely, it's a very very cool idea. And we have thought about this. We couldn't really get around this yet.
I actually also have a question on this first part, second part of the first part, where you do the adversarial examples. This reminds me a bit of what Matthias talked about this morning about like biases towards texture rather than shape. Do you see a connection there? Do you know what would happen if you would just randomly texture those shapes?
Well, in a way, we do this, right? So I mean, first of all, the connection is an interesting one, but in a way, we're preserving the shape for the most part, right? So we're leaving the shape essentially there for now, right? There's slight modifications, but really the shape is there for the most part. So we basically mostly manipulate the texture at this point. And in that sense, yes, you're right. So in that sense, it's another instance of showing that actually the texture dependency is too strong at the moment, and shape is not used as much. But even, yeah, exactly. Maybe that's actually the right way of putting it.
Yeah, thank you very much for your very interesting talk.
Cool. Thank you.
Next up, we have Sio Tang. Sio is an assistant professor at ETH Zurich. And she did her PhD at the Max Planck Institute for Informatics and Saarland University in 2017 under the supervision of Bernt Schiele. And after that, she received an early career research grant and started her own research group at the Max Planck Institute for Intelligent Systems. And then since 2020,